Hello everyone, this is the first lecture in the series on number theory. This is the first video out of 25 planned lectures. The textbook is an introduction to number theory by J.H. Hardy, and without further ado, let's just get into the video, let's just get into the lecture. So first of all, let's talk about divisibility. Although this is a video or a lecture on the series of primes, and so is the next one, but in this particular lecture we're just going to lay the mathematical background that we're going to need for the series of primes. So first of all, we're going to talk about divisibility, and we'll introduce some more interesting ideas as we go on with our lecture. Okay, so first of all, an integer a is said to be divisible by b by this little expression, b divides a. So this is how we read this, b divides a. And thus, of course, 1 divides a and a divides itself, which makes sense. And finally, b divides 0 for all numbers b except 0. Okay, so now we'll just see some corollaries that are going to be all interesting. So if b divides a, so a being the larger number, b divides a, and c divides b, so c is the smallest number of a, b, and c, so that just means that c divides a. And this is silly, but we're going to take an example. So 9 divides 27, and of course we know that 3 divides 9, and of course 3 divides 27. This is silly, and we'll know why later on. But anyway, again, if b divides a, then that just means that BC divides AC. So if B divides A, then any multiple of B divides any multiple of A. And again, this just makes sense. If A or if C does not equal 0, and well, C divides A and C divides B. So if C divides A and C divides B, then C divides MA plus NB. And also that makes sense. You can try that out on your own, because you'll get more intuition if you try things on your own. Anyway, let's just see the formal definition of a prime, and then we'll start getting a sense of what we're talking about. So first of all, formal definition of a prime. First of all, numbers are, well, let's just talk about integers. Integers are divided, or non-negative integers are divided into 3 categories: composites, and of course primes, and of course the unit 1. So 1 is not a composite, and it's not a prime. Okay, so which brings us to our first point. Say the prime is p. So p is greater than 1, and 2, p has no divisors other than itself and 1. So which makes sense. So we have 2 is a prime, 3 is a prime, 5 is a prime, 7 is a prime, and so on. We'll get to the series of primes in a second, but let's just take our first theorem. So theorem 1: every positive integer other than 1 is a product of primes. And this is actually this is really easy. and we'll prove that by induction. Okay, so proof by strong induction, to be specific, but it doesn't matter. So our base case is, of course, it's not 1, so the first number after 1, or the first integer after 1 is just 2, so p2, and in the case of p2, well, 2 is a prime, so it just makes sense that in the case of p2 it's true, since 2 is a product of 1 prime, which is itself. Okay, so we're not gonna try p of 3, and again it's the same thing. It's 3 is a product of 1 prime, which is itself, and so on. But let's just see that our inductive step. So our inductive step is just for n. Suppose our assumption. So let's just assume that our assumption, or suppose that our assumption is true for n greater than or equal to 2, and for an I, which is a product, which is a product of primes, where 2 is, hold on a second, 2 is less than or equal to I, and again less than or equal to, or just no, n plus 1. Okay, so we have just said less than or equal to n, but it doesn't matter, same thing. So this is our inductive step. So okay, now to actually prove that p of n plus 1 is a product of prime, then we have two cases. The first is p of n plus 1 is a prime, then there's nothing to prove, since n plus 1 is a prime, so it's a product of a prime, which is itself. N plus 1 is a product of 1 prime, which is itself. So okay, the second point, or the second case, is just n plus 1 is not prime. Okay, by the way, okay, n plus 1 is not prime, which by definition means that n plus 1 is k times m, or k dot m. Anyway, such that again 2 is less than or equal to k, and m, which is less than n plus 1. Okay, so now by our induction hypothesis, k is prime, and by following the same logic, m is also prime, then it is the case that n plus 1 is also, not also a prime, is a product of primes, which proves our point, and this was our simple proof of induction. There is also another way to prove this by contradiction, but we'll try to get to that later on. So okay, fp is prime, and b divides ab, then b divides a, or p divides b. This is just a little theorem, and of course there's a corollary. Let's just say that this is a theorem, and the corollary is just fp is prime, and b divides a, b, c till n, or whatever, then p divides a, or p divides b, and so on. Okay, so here's the thing, this is very important. So the sequence of primes as you know, 2, 3, 5, 7, 11, 13, and so on. But how do we actually get a table of or the series or sequence of primes under a specific number? So okay, there is a method called Sieve of Eratosthenes, and here's how it works. We get all the numbers 2, 3, 4, 5 up to our n, and then we do this. We eliminate 2 power 2 and any other multiple of 2. Then we eliminated or got rid of even numbers, and then eliminate 3 power 2 and its multiples, or multiples of 3, and then eliminate 5 power 2, and of course not 4 power 2 because 4 had already all even number are taken care of, multiples of 5, and so on until you're left. The numbers you're left with are the primes. So okay, and now that when we get the table of prime numbers under 1,000, or prime numbers under 1,000,000 or 10,000,000. By the way, the number of prime numbers under 10,000,000 is 664,579. But the tables indicate something. Indicate that the number of prime numbers is just infinite. Numbers is infinite, which gets us to our next theorem, which is Euclid's second theorem. The number of we don't really have to write that. So we're gonna take a little break and introduce some notation, which is going to be very useful. And if you have worked with algorithm analysis, then you're familiar with some of these and possibly all of them. So okay, first of all, we have big O, little o, asymptotically equivalent, and these lovely boys. Yeah, we're gonna say exactly what they mean, but just hold on a second. So these are notations, little notations, and we're going to define them exactly what they mean. So f, a function f, this is not equal, this is order of big O of some function phi. Okay, then what that means is f is less than a, which is a constant by phi, which is the definition of which is also the definition of the big O notation in algorithm analysis. So we have function f. Let's suppose that the function is f of n. This is an example. F of n equals n squared. Then now let's suppose that phi of n is n cubed. So now this is the case that f of n is order big O of phi, which is the case that n cubed is the upper bound for n squared. And by the way, n squared is the upper bound for n squared, but we'll see that in a later video. But I hope that you got the basic idea. Anyway, number 2, if f equals little o of phi, then that means the limit, hold on a second, okay, the limit where x or n, doesn't matter, approaches infinity, okay, doesn't matter, it's somewhere here, so it doesn't matter, hold on a second. Anyways, let's just say this, it approaches infinity, where, you know, the fraction of f over phi, the functions, of course, well, this is just going to equal what? This is going to equal 0, because here's the thing, phi is an upper bound for f. Then we have, let's just take an example, okay, just copy this, and here is the thing, same example, n squared over, then now when we substitute n with infinity, so we're left with 1 over infinity, which just is 0, because 1 is infinitely small, way smaller than infinity, so it just follows that it's 0. So okay, our final notation of the first group is just this little guy, which is asymptotic. By the way, these are mostly equivalent, but we'll get to that. So when we say f is asymptotic to phi, that just means that f over phi equals 1, okay, and this is just really simple. Now we'll just get to some examples that will going to make us have a feel for these notations or get the idea more. So x is big O of x squared. This is just a very basic example because, well, x squared is an upper bound for x. X equals little o of x squared. Okay. Now, 10x is O of x, because, well, big O algebra just lets us ignore the constants, so since 10 is a constant, then it's big O of x, and this is very important. Sine of x is just big O of 1, and what does that mean? That just means that it's a constant function, because well, here's the thing, because sine x, the function of sine of x is between -1, just going to result in something between -1 and 1, so it's just a constant. No matter what it yields, it's just going to be a constant. Now, these are this is the case where x approaches infinity, okay? But we're gonna say something a bit controversial here. X squared is big O of x. What are you talking about? Just hold on a second. And x squared is little o of x. Hold on. Okay, little o of x, and sine x is asymptotic to x, and 1 plus x is asymptotic to 1, where x just approaches 1, sorry, 0, I'm sorry, not 1. So, which makes sense, because if x is really infinitely small, so we're not gonna notice anything about the asymptotic growth or functions that are not gonna be different, but which is why it's the case in computer science when we analyze algorithms, we tend to we make x tend to infinity. We only care about the edgy cases where we have an array of billions of things that we wanna search. Anyway, not the point. Okay. So we finally come to this. So this is. I'm sorry. No. Okay. Yeah. So f is not dominated by phi. Just means that f, and this is just really silly, f over phi limit for x tends to infinity. This is just going to equal 0, which is equivalent to what? It's just equivalent to little o of x. I'm sorry, a little o of phi, I'm sorry. So, okay, because well, phi is little over f. I just defined that a little earlier. So now f is dominated by f just means that the limit where x approaches, let's just copy this, but this time it's just going to be infinity. So f is actually greater than phi, so this time it's different. So f is asymptotic. Okay, so this is just the order of magnitudes to phi. That just means that, well, if we have a, so hold on a second, a, which is a constant, by phi is less than f, which is less than a by phi. And yes, we used a in both cases, but it just means different a's. Okay, these are not the same. So okay, finally we get to some really very simple things, and then, as I said, the equal sign does not mean, in the case of big O and little O, or the big O algebra is not really symmetrical, and little o is stronger than and implies big O of n, but it's not usually the case. It's not vice versa. Okay, so now let's just say that, so this is very important. Suppose that P, let's just use the notations we just introduced. Suppose that P is some property, like that number is a composite, and we'll get to that just in a second, as some property of the number x. Okay, now and P of x is the number of numbers not exceeding or less than x which possess the same property. So okay, so P is P is some property which is a composite of the number x. So x is a composite, and P of x, the function P of x, is the number of numbers, the total number of numbers less than x which possess the same property. Then first of all, fp of x is asymptotic to x when x approaches infinity. So then that just means we can just simply say, well, almost all numbers possess that same property, because we just introduced some notations. So we just said, okay, well then if it's big O of x, or now it's not big O of x, it's asymptotic, almost the same number. Okay, then we have a billion numbers. And now we're saying that it approaches infinity, and most of them, or the numbers really very close to the infinity, then we can just say, well, almost all numbers are composites. And that's mostly the case, but we'll get to that. Now let's just introduce some notations that we're going to use for the rest of the video and the next lecture. Then, okay, if we have pi of x, that just means the number of primes less than or not exceeding x. If it's little o of x, so that just means what we just said, that almost all numbers are composites. So now here's the thing. We're going to introduce the logarithmic function, because logarithms, the study of logarithms and the properties of logarithms are very important for the study of prime numbers. Now, okay, since and by the way, things that I did not provide a proof for are going to be discussed in either the next video, or they're going to have separate videos. Anyway, e power x, equals 1 plus x plus okay, plus fraction x power n over x factorial, and so on. Okay, so here's the thing, here's what we mean by this. I'll just combine this, and then we get x power negative n e power x by d power x is greater than the fraction x over n plus 1 when x approaches infinity. Okay, and that number of course is infinity, so again it's big, it dominates, x dominates n plus 1 factorial. So okay, anyway, hence e power x tends to infinity faster and more rapidly than any power of x. So now this is very important. What is the inverse function of e? Well, it's the natural log. So okay, the book refers to the natural log by log, which might confuse some people, since log is usually referred to, well, sometimes it's log to the base 10, and in computer science log to the base 2, but now, well, it's log to the base e, which is 2.7, but not the point. Okay, so here's the thing. It follows that log, so we're going to follow the book. We're not going to say that it's we're not going to write it ln, but just know that it's the natural log of x. Well, it tends to infinity much slower. Okay, then okay, so now when we say that log of x, which this is really important, log of x over x power c, for example, then now this approach, this is infinity. So I'll just say that this is infinity, which is the definition of two things. The definition of, because they're equivalent, it's little o, and that it's not dominated, okay? So now, what this means is, well, the logarithm or the natural log of x approaches infinity much slower than any power of x, which is the exact opposite of what we just said about e, because we said, well, e approaches infinity much faster than any power of x. So now here's what, so of course for any constant c, but not the point. So okay, and again, if we take the natural log of the natural log, then okay, let's see this. So okay, log of 10 power 9 is 20.72, but which is really slow, because it's approaching infinity really slow. But the natural log of 10 power 9, well, in this case it's just 3. Now let's be rather silly and say, well, the natural log of 10 power 1000, well, what's that equal to? Well, it's equal to a little bit greater than 2. Don't try that on your calculator, but anyway, because it's not really going to be able to work it out. But anyway, so again, we introduce a new theorem: the number of primes not exceeding, which is less than, x is asymptotic to x over log, or the natural log again of x. I'm gonna stop saying that, but you better remember it. Okay, so here's the thing. The pi of x is asymptotic to, and again, pi of x is just the function of the series of primes not exceeding x over the natural log of x. Okay, so now, well, this is equivalent to this theorem, which is Chebyshev's theorem. Okay, the number, or the order, hold on a second, the order of magnitudes of, well, pi of x is really asymptotic to x over log x. These are equivalent, okay, but it's very important that we know both. So okay, the number of primes less than 2 power 3 is actually 168. But when we do this, when we try our little theorem, x over log x is actually 145. So okay, dividing both, the ratio is equal to 1.159. So now, okay, let's try a few more. 10 power, the number of primes less than 10 power 6 is 78,498, but now our function yields 72,389. Now the ratio is 1.84. Okay, well, that's much better. Okay, so now less than 9 is just 50,847 and 534, but our function yields 48, 254 and 942. Okay, Now the ratio is 1.053. Okay, so now it yields an approximation, not a particularly fast or rapid one, but well, it's very good approximation of the number of primes not exceeding a specific number. So now this is enough for this lecture. This lecture we spent most of our time introducing notations, some ideas. We're going to get into more detail in the next lectures, and the things that we did not provide proof for in this video, we're actually going to do that in later lectures or little videos. And good luck.